Okay, so the next example I want to describe of statistical mechanical system is a little bit artificial, but I think it's interesting. So now our configurations is again we are again considering n a string of n variables, but now let's say that xi is we are looking at the gas, and xi is the number of particles of the gas on site I. So we have a system of say n sites. They can be arranged in different ways. On each of these sites you have a certain number of particles, and these particles can move say from one site to the other, and so you have this gas of particles that moves along on these sides, and n is the number of sides. And so the total number of particles, which is the sum from I equal 1 to n of the xi, let's say that this is fixed because when one particle moves from one side to the next, then I mean this conserves the total number of particles. Now we also assume that these are weakly interacting particles, in the sense that particles interact only with the other particles on the same side. Okay, so and we are going to assume that the energy is given by the sum of all sides of the logarithm of 1 plus the number of sides, the number of particles on that side. Okay, so why is this an attractive, weakly attractive interaction? Well, consider two sides, and then you will see that, say, if I compare the energy of the system where site I contains xi particles and site j contains j particles. If I now move all the particles on site j on site I, then the energy will become over 1 plus xi plus xj. So the change in energy, if I move all the particles from site j to site I, is going to be minus this plus this. And you see, because of the convexity of the logarithm, then this is negative. Okay, because well, the logarithm, so the energy as a function of the xi is a convex function. So the log of 1 plus x, well, this is because just 1 plus xi times 1 plus xj is larger than 1 plus xi plus xj. Okay. okay? And well, this is trivial, okay? So these are particles that like to be together, okay, on the same side, because being together lowers the energy, and states of lower energy have a higher probability. Okay, so now let's consider the statistical mechanics of this system. So let's compute the partition function. Okay, so now in the calculation of the partition function, so I can take a sum over all so this sum is a sum such that this object is fixed. And so I can write this sum as a sum over all possible, say, over x1 from 0 to infinity, sum over xn from 0 to infinity, of well, the e to the beta times the energy is just the product I from 1 to n of 1 plus xi to the power minus beta. Okay, and then this condition that this is fixed, I should put it as a delta function, that the sum over I from 1 to n of the xi is equal to n. Okay, now I can introduce integral representation of this delta function, which is just the integral dk over 2 pi minus pi to pi of e to the I k n minus sum over I of the xi. And if I do that, I can rewrite this as the integral from minus pi to pi dk over 2 pi e to the I k times n, and then I have so all these sums can be factorized, okay, and so I have a small n, product of small m sums that are all the same, okay. So what I have is a sum from x from 0 to infinity of 1 plus x to the minus beta times e to the minus I k x. Okay, and this is raised to the power n. Okay, and now this can be written in the form of an integral dk over 2 pi of e to the minus n times a function g of ik. Let me write it in this way, where this function g of z is, there is n divided by n, which is the number of particles per site, okay, times z, which is this term here, and then there is plus, oh sorry, there is a minus sign here, so let's take a plus sign, okay, and then there is plus the log of the sum from x from 0 to infinity of 1 plus x minus beta e to the minus z over x. Okay. Now, well, let's, so this integral will be dominated by the saddle point, and the saddle point condition is when the first derivative of this function is 0, which is n divided by n, and here there is a minus, is a sum on x from 0 to infinity of 1 plus x to the minus beta of e to the minus z times x, and then above I have the same sum of 1 plus x to the minus beta times x times e to the minus z times x. And this should be equal to 0. Okay. Now, what is the feature of this solution? So this should give you a z star, and then the partition function should be essentially given by e to the n times g of z star. Okay. Now, what is this? What is this z star? So first of all, you see that the solution of this problem is a solution of which is essentially consists of studying the statistical mechanics of just one site with x particles, and where now the energy, so where now so this reduced problem is the statistical mechanics of say one site with an energy that depends on the number of particles on that site, x, which is equal to log of 1 plus x minus plus z over beta times x. Okay. So you see that this is a similar problem to this one. The only problem is that here you don't have a constraint on how many particles should be on this site, but you have this additional term on the energy that tells you that now your energy actually increases. So this, if you want, this is an attractive force this is a repulsive force for particles, because it tells you that the derivative of the energy with respect to x, which should be minus the force, is equal to z over beta. So this is a negative. So it's a force that draws x to 0. Okay. And so your initial say potential was just this log of 1 plus x. Now it is increased. Okay, by this term here. And so this means that if so this means that this z imposes a force towards x equal to 0. So this z is essentially enters as a chemical potential in this system, and it mimics essentially the fact that the particles on this site can also go to other sites, and so the propensity of particles to leave a particular site is this chemical potential. So, and it acts like a force that puts that reduces X. Okay. Now, very good. So, what we have to do is just to look at this reduced problem and to find the Z star such that, say, this condition is satisfied. So if you look at this condition here, this condition is telling you that n divided by n is should be equal to the expected value of x in the equilibrium of this problem, because essentially this is the partition function of this reduced problem, and this is the average, the statistical average of x on this reduced problem. So this is essentially the expected value of over this reduced problem of the number of particles on this, and this is the condition that gives you Z star. Okay, this makes a lot of sense because it is telling you that say you want to fix this chemical potential in such a way that the expected number of particles on any site is equal to the average number of particles. Okay. Okay, so let's see how this solution works. So let me rewrite it here, and this is the sum over x from 0 to infinity of 1 plus x minus beta times x e to the minus z times x divided by sum over x from 0 to infinity 1 plus x minus beta e to the minus z times x. So what I want to do now is to plot as a function of z the left hand side, the right hand side of this equation, so this object here. And so of course z must be positive, because otherwise this is going to be infinite. For negative z this partition function does not converge. Okay, so so let me plot as a function of z this expected value over beta of x. Now there are two solutions. So you see, so let's say that so this will be a decreasing function of z. So it will be a function that decreases. So, but for z which is equal to 0, so the value at z equal to 0 of this function will be equal to infinity if beta is less than 2. Okay? So if beta is less than 2, then you are going to have a function that looks like this. Okay, so this is for beta less than 2. So it's a function that when z goes to infinity, you see this is a decreasing function of z, so it will go to 0. And when z goes to 0, this sum diverges. Okay, so it tells you that no matter what is the density that you want to achieve, there will be, you can find a value z star that solves this equation, and then you can get the solution. And the solution will look like a solution where essentially on each of these sites you have a number of particles which is essentially independent and identically distributed with a distribution that is given by the solution of this reduced problem. Okay? So this is an homogeneous solution of a gas that, of particles that travels around, and for any density, for any value of n, you can find a solution of this type. Okay. Now let's look at what happens at small temperature. So for beta, which is less than 2, instead, this when you set z equal to 0, this sum attains a finite value. Okay, so then is beta less or equal to 2. Then for beta equal to 2, less than 2, then this curve will just reach a finite value here, where this value here, we can call it, say, this value, we can call it a rho critical of beta. Okay? Now it is clear that, say, if your density is less than this critical rho, then you can find again your z star, and you can solve the problem, and the solution will look like the same. Okay? But what if your n is larger than n star? Then there is no solution. There is no solution to this problem. Because I mean, this solution cannot accommodate more than rho critical particle per site. Okay. Now the solution to this problem is that essentially we have already seen this problem. So this is exactly formally the same problem that we have discussed when we discussed large deviations with fat tails. When beta is very large, you can check that say the most likely way in which you can realize a state with a density which is larger than this critical density is to have all the particles being distributed on the other side with a density which is the critical density for that particular temperature. And then on one side you have a finite fraction of all the particles that just pile up on one single site. Okay? And this is the same phenomenon of spontaneous symmetry breaking, because you see that when the density is smaller than this critical density, all the sites have the same distribution, but above the critical density there is one site that is special, that there's a finite fraction of all the particles. Okay? And so if you want to draw the phase diagram, so as a function of the temperature, say 1 over beta, or say as a function of beta. So if you plot this rho critical of beta, then you have a situation like this one, where this rho critical diverges at beta equal to 2. So you have two regions here. So one region where you have a symmetric phase, where your gas is homogeneously distributed on all these sides, and say an asymmetric phase where when the density is larger than this critical density, where essentially there is one site where all the particles just condense there. Mathematically, if you look at the conditions for this condensation, it's mathematically the same condition for Bose-Einstein condensation, although a Bose gas, a Bose ideal gas, is very different from this realization. But if you look at what is the condition for which you get this condensation of finite fractional particle in the same state, then it is essentially the same mathematics that describes both phenomena.